Hello, class! And I just wanted to do a brief summary of what this unit is. So, the key notes I put on this one piece of paper, so hopefully you can follow along and then just supplement it with the notes from the PowerPoint for lesson 4 and 5. So for lesson 4, which is the front of the worksheet, and this is worksheet 9.4, drawing, the drawing side, just the front, the main thing that you need to know is that the voltage is equivalent to still potential energy, but voltage is specifically the electrical potential energy. So it's very similar to gravity, where if you have something and you let it go and it falls towards the ground, opposite charges attract. So the further away they are, the more energy they have. Just like dropping something from a higher height and it falls to the ground, it'll hit the ground harder the further away they are. It takes energy to lift something up. So separating opposite charges takes energy to separate. So the further away opposite charges are, the more energy they have. Because they attract, it takes work to separate them. For like charges repel. So it's like two north poles of a magnet. When you push them together, they want to repel and push away from each other and pull apart. So since like charges repel, it takes energy to actually bring them together like two north poles of a magnet. So the closer like charges are to each other, the more energy is built up. And then they'll fly off when it's finally let go. The next key part is what happens with parallel plates. And the big thing for parallel plates is that the electric field, since these lines are equally dense, that means the electric field is actually constant between them. Remember, electric field's drawn from positive to negative, and density equals strength. This density is constant. So since the line density is constant, that means the electric field is constant. But don't forget this equation from last week. Electric field is equal to force per charge. So if the electric field is constant, that means the force is also constant. So for oppositely charged plates, the electric field is constant, the force is constant, so it's going to have the same force the whole way as it moves across. If it switches signs, and both plates are, say, for example, positive, if both plates are positive, this plate will have lines coming out of it, this plate will have lines coming out of it, and just like vectors, a vector going this way and a vector going this way cancels, so there'll be nothing in the middle. This is actually what the lines look like if it's two positive charges having an electric field drawn. Notice how there's nothing in the middle, so there'll be no force in the middle of this electric field diagram. Now we're going to switch over to the back. And the key part to the back is that voltage is positive for positive charge, and voltage is negative for negative charges. So I'm going to draw just one diagram for a positive point charge first. This is a 5 volt point charge. So right on the charge will be 5 volts. And that's the amount of potential energy. In our example, on the back, I start with topographic maps. This is very similar to something that's going to fall down the hill. If this is 5 meters, 4 meters, 3 meters, 2 meters, 1 meter, something will fall down the hill. So that's why I start with a topographic map for my example. 5 meters, 4 meters, 3 meters, 2 meters, 1 meter, something will fall down the hill. So as I go away from a positive charge, my voltage goes down. That's also true for this example. Notice how there's a 20 volt difference. There's a positive charge and a negative charge. So if there's a 20 volt difference, to be a difference in two equally in magnitude charged objects, one will be 10 and one will be minus 10 to have a difference of 20. So going from the positive to negative is a voltage difference of negative 20. Going from negative to the positive is a voltage difference of positive 20. This is very similar to the last questions on the back, where you have to draw out what voltages they are. So question 13, 14, and then question 17. For this 20 volt difference, for a positive and negative, exactly in between them will be 0. And halfway between the 0 and a 10 will be a 5 volt, and it goes all the way around. And exactly between the 0 and a negative 10 will be a negative 5 volt all the way around. Going back to the mountain example, for the 5 volts, that's a high voltage, and then it goes down to 0. So you can think of it as the top of a mountain. I'm going to draw it out as a profile. You can think of this as like a volcano shape, where this is the positive 5 volt. Maybe this is the 4, 3, 2, 1. So you can think of this as 5 meters, 4 meters, 3 meters, 2 meters, 1 meter. And this is looking at it from top down. This is looking at it from the side. This is like a mountain where it's high at 10, and it goes down to 0 meters, and then it goes into a hole. So let's draw what that would look like. So we have our mountain on this side, and then it goes down to 0, but then it actually goes into a hole. So it would be 10, maybe 5, 0, negative 5, and then down here, negative 10. Where this, I'm going to treat as my 0 voltage line. Again, all these are volts. Just remember the rule for why we're doing this. Remember, this is all drawn, electric fields and how things fall are drawn in the direction a positive charge would move or would be forced. So for this, the way I would draw this for where a positive charge would be forced, obviously a positive charge would fall down the hill, coast, and then fall in the hole. So I hope this helped you out. Please text me or Schoology message me or ask for a help session if you need it. And good luck this week.